So question number 1 is acceleration question. Okay, we're just looking for the initial velocity on that one. All right, so I don't have it actually done. I'm gonna have to do some work. Okay, let's do this. Okay, so I've got an object that reaches a speed of 29 meters per second. So VF is 29 meters per second. After accelerating at 7 meters per second for 2.9 seconds. Did this question look at all familiar to anybody? Good, it should have because you've done it before. Sometimes I get lazy and do that. Okay, all right, so we've got our 3 givens here, and we're looking for VI. So give them 1 mark for that. Okay, give them 1 mark for identifying it as an acceleration problem. Okay, that's the formula they're going to have to use. We need to manipulate for VI. So we're going to multiply both sides by t. Then we're going to add VI to both sides. And then we're going to subtract t times a back over to the other side. So we got VF minus t times a. Give them a mark if they have that for their formula. All right, and then we need to plug in our numbers. So VI is going to equal 29 meters per second minus 7 times 2.9. minus 7 times 2.9. All right, so we should have a an initial speed of 8.7 meters per second. Boy, everybody better got that right because you did that one on Tuesday. Yes, it is because this has 1 significant digit. So yeah, if they did round to 9, that would be fine. There's only 1 significant digit in this question. That's actually what the answer should be. Okay, second one. Okay, so in this question, we have a box that has a mass of 8.5 kilograms, so we know what M is, 8.5 kilograms, which tells you it's not an acceleration question because you never get mass in an acceleration question, okay, is lifted above ground level. All right, if 183 joules of work is done, how high does the box get? What's my initial height? 0. All right, so there's what I have. What kind of energy is being changed in this question? Potential energy. The box is being lifted. It's not being accelerated. Its kinetic energy is not changing, right? Only its potential energy. So, okay, give them a mark for their givens here. Okay, we're going to treat this as a work energy theorem question. So work is a change in potential energy. All right, our work is 183 joules, so we don't have to do force times distance at all here because they told us what work was. All we have to do is figure out the change or use the change in potential energy to help us find the height. Okay, so change is final minus initial, m times g times h final minus m times g times h initial. And what is this? 0. All right, so if they have that work equaled the potential energy, or they have something like this, give them a mark. That's their second mark for identifying that it was a change in potential energy that was going on in the question. Okay, we need to manipulate for final height. So we're going to divide both sides by mg. Okay, and we're going to be left with HF equals W over mg. So if they have that, or they went straight to plugging in the numbers, okay, that'll be their third mark. Okay, so if they either have this or they have this. Okay, that's their third mark. Okay, 183 joules was the change in potential energy, the work done. Okay, and on the bottom we have mass times gravity, 8.5 times 9.81. So when we do that, okay, we have 183, whoops, not 83, 183, divided by, in brackets, 8.5 times 9.81. All right, so we're going to get 2.2 here as our height. 2.2 what? Meters. That's their fourth and final mark. Questions on that one? Yeah, 2.19 is fine. Okay. Any other questions on number 2? All right, give him a mark out of 9, and I want him handed in over there in front of Sean. Okay, where we left off yesterday was I ran out of time just before I was about to reveal the not so exciting answer to this question. Okay, so we were looking for how much work would be done in carrying this package from the 10th floor to the, from the 3rd floor of a building to the 10th floor of the building. Okay, so what we had to do was say that work was equal to the change in potential energy, which is exactly what our last quiz question was like, except that our initial potential energy on the quiz was 0. Here it isn't. Okay, here it does have some potential energy at the beginning. Okay, and that's where a few people came up and asked me, Mr. Coder, is it okay if I didn't include the work part in my problem solving on the quiz? And it is, as long as the initial potential energy is 0, because then your final potential energy is the work that's done, okay? And that works out. In this case, it's not going to be the case. We have to actually do the subtraction operation here, okay? So we have to go m times g times h final minus m times g times h initial, okay? If you're a math whiz, you probably figured out that you really don't have to do it this way, that you could probably shortcut like this. If you're traumatized by what you see, ignore it. I'm going to do it the other way anyway, okay? But if you're a math whiz, you probably noticed that you could do that, okay? Which would also be fine, okay? All right, so I'm going to plug in my numbers here. The package was 10 kilograms, right? 10 kilogram package, and we're going from 30 to 100 meters. Okay, so 10 times 9.81 times 100 minus 10 times 9.81 times 30. Okay, so when we plug that in, okay, if you're taking the shortcut, then you're going 10 times 9.81 times 70, and you're getting this number. If you're doing it this way, which is also fine, okay, then you're going to have 10 times 9.81 times 100 minus 10 times 9.81 times 30. Whoop, won't give me the same answer if I don't type it in right. Okay, either way works, right? Our work done here is 6,867 joules. Uppercase. All right, questions on that one? Okay. So what did we say was the first thing you need to do when you think you're looking at a work energy theorem question? Figure out what kind of energy is being changed by the work being done. Okay, that's the first step. Once you know that, then it's just work equals the change in either potential or kinetic. And that'll be fine for Science 10. When we get on to Physics 20, then it'll always be the same thing. It'll always be work equals the change in mechanical energy, and it'll be both kinds. Okay, actually makes it a little easier because you never have to worry about which kind is changing. You just plug them both in. Okay, if one doesn't change, it just ends up being 0 and you're fine. Okay, try that one. I want you to write that example down and give it a try. Okay, first step, figure out what kind of energy is changing. What kind of energy is changing? Kinetic energy. The speed of this truck is increasing. All right, so work is being done by the bulldozer. It's increasing the kinetic energy of the truck. All right, so what we're going to write down here, we've got VI to be 2 meters per second. We know the mass of the truck is 2,500 kilograms. We know we're looking for VF. We don't know what it is. Okay. But we know that the bulldozer does 7,500 joules of work, which actually makes this question a little bit easier because I didn't have to do force times distance on it. Okay, they already did that for me. Okay, so I've got these numbers here, and we've already said that the work being done is changing the kinetic energy of the truck. Everyone all right with that? Okay, so that means that work equals the final kinetic energy of the truck minus the initial kinetic energy of the truck. Okay. I'm looking for final speed. So what term is that part of? Final kinetic energy. So I'm going to want this term by itself. Agreed? So what should I do with this? Add it over here. Okay, so I'm going to go work plus the initial kinetic energy equals the final kinetic energy. Okay, now I'm going to expand it. Sometimes it's easier to move a few things around before you expand them. Okay, and by expand, I mean write the whole formula in. All right, so I've got work, which I'm not going to write a formula for because I know the actual value of it over here. Okay, plus 1/2 times m times vi squared equals 1/2 times m times vf squared. I want vf by itself, so what do I have to move? Half of m, right? I'm multiplying these three things together, so I've got to move these two things. Okay, the half m doesn't cancel because there's an operation on the top already. Okay, I want vf, not vf squared, so I need to square root both sides. Okay, does everyone follow my manipulation there? Okay, where did I lose you? Okay, so this is the formula for kinetic energy here, right? For EK. I just plugged in the formula for EK here. Okay, because I had it written that I was going to add EK to work. I know what work is. It's 7,500 joules. I don't know the number for EK, so I have to use the formula to find it. That's why I plugged it in. Okay. All right, so now I'm going to plug in my numbers here. Okay, so we're going to have 7,500 joules, the work that was done, okay, plus the initial kinetic energy of the truck. Okay, if I take the work, the change in energy, and add it to the initial energy, that should give me the final. Agreed? Okay, that's kind of what we're saying here. All right, so plus 1/2 times 2,500 times 2 squared. And I got to divide that by 1/2 times 2,500. Okay, that is going to give me, once square rooted, VF. Okay. All right, so I'm going to do this piecemeal rather than plugging it all in at one time. So I'm going to have 7,500 minus 0.5 times 2,500 times 4, which is 2 squared. Whoops, sorry, plus. Okay, so I have 12,500 joules worth of kinetic energy at the end. Okay, I want to divide that now by 1/2 of 2,500, which is 1,250. All right, so I've got 10 there. Okay, and then I need to square root that. All right, so the final velocity of the truck, or final speed of the truck, sorry, is going to be 3.16 meters per second. Did the tractor have to do a lot of work and not really get a lot out of it? It did. Okay, had to do a lot of work and didn't get much out of it. So 3.16 would be my final speed. Okay. Everybody all right with that? Okay, all I did there was I expanded out the formulas. Instead of writing just EK and EKI and EKF, I put in the 1/2 MV squareds for both. Okay, then I started moving things around. Once I had everything expanded, then I can move individual things around and start solving for them. Okay, again, that's about as difficult as they're going to get in Science 10. Okay, most of the time they're a bit more straightforward than that. All right, so steps here. I know sometimes people like to have a set of steps when they're first starting out, okay, doing things. This isn't in your notes package, so you might want to write it down, okay, if you're a steps person. Solving work energy theorem questions involves first out, writing out the givens, okay, and then identifying the type of energy being changed, okay, and we've said that like every time we've started a question, identify what kind, okay. Is it potential energy? Then I'm dealing with MGH. Is it kinetic energy? Then I'm dealing with 1/2 MV squared. All right, once I've identified what type of energy is being changed, then I want to set up the work energy theorem. Okay, that is work is a change in energy, and plug in that either work, if they actually gave me the number of joules, or force times distance equals the final energy minus the initial, whether that's potential or kinetic. Okay, so EF minus EI. Okay, so if it's kinetic, it would look like this. Force times distance equals 1/2 MVF minus 1/2 MVI. Okay, if it was potential, it would be FD equals MGHF minus MGHI. Okay, then you manipulate and solve. Okay? There really aren't that many steps, but some of the steps involve you really having to read through the question carefully and get what you need from it. Okay, so give this one a try, guys. We got a person who uses an unknown force to lift a 50-kilogram mass to a height of 1.5 meters. Okay, how much force was used? Okay, guys, it doesn't actually ever say anywhere outright that it was lifted off the ground, but where is height always measured from? The ground. Okay. Okay, what kind of energy is being changed? The potential energy. Okay, I've already got my givens written down, and so I didn't skip that step. Okay, givens are written down here. Okay, the distance and the height in this question happen to be the same. When you lift something, that's the distance over which you exert the force. So D and H in this question, anyway, because it's from the ground, are the same number. Okay, so what we've got here is that work is a change in potential energy. Okay, and really all we have to do is calculate what the potential energy at 1.5 meters is, and then divide by 1.5 meters. Okay, so here's what we got. Force times distance equals m times g times hf. I'm not putting mghi in there because mghi is 0. All right, so I want to find the force that was used, so I divide both sides by the distance. When I do that, if I'm really on the ball, I notice that hf and d are the same number. So what do? So really, the force is equal to the force of gravity, m times g. If you look on your formula sheet, you're going to see this formula on there. We almost never use it, but it's there. Okay, the force of gravity is mass times gravity. What that calculates is your weight. Okay, the force of gravity is your weight. Everyone follow there? Okay, that's why I was saying the other day, people are saying, oh, but you need their weight. I'm thinking, no, you don't. You need their mass. Mass and weight are two different things. Okay, mass is how much of you there is. Your weight is how hard does gravity pull on how much of you there is. Okay, obviously, if there's more of you, gravity pulls with more force because there's more of you. Okay, not with greater force, not with greater acceleration, but with greater force. Okay.
50 kilograms. I thought that was weight.
No. That's what we say it is, but it isn't. Okay, we have this again. This is another problem we have in North American culture. Okay, where someone asks, "Hey, how much do you weigh?" Or, "Oh, I got to lose some weight. I got to lose like 2 kilos." Well, no, you got to lose 2 kilos worth of mass. I could lose 2 kilos worth of weight by going somewhere else. Okay, in fact, if I went to the moon, I'd weigh 1/6 what I weigh here, but there wouldn't be any less of me.
How do you measure kilograms?
Kilograms is mass. Kilograms is mass. Weight is not measured in kilograms, but that's what we always say. When we step on a scale, it tells us our mass, but we say our weight. Okay, but we're wrong. What I'm saying is the way you've been taught all the way along is wrong. Okay, your mass and your weight are two different things. The scale that you step on has a spring in it. When you step on the spring, your weight, that is the force of gravity pulling your mass downwards, compresses the spring. The scale shows you what your mass is by using what your weight did. Okay, with me there? Weight is a force, therefore it is measured in newtons. Mass is measured in kilograms because it denotes how much of something there is.
If you took a scale on the moon, would say that you're doing mass.
It would, because the scale is calibrated for your weight on Earth. Okay, it is calibrated to use the acceleration due to gravity on Earth to give you an accurate weight. Okay, like really accurate scales have to be calibrated to their location on Earth because you actually weigh different amounts in different places on Earth, right? We talked about the yesterday where the Earth isn't perfectly round. Yeah.
When we were solving this, we did like work equals and then figured out what the work was and then manipulated it for force and distance, like did 2 steps.
Yeah. What you did is the same thing I just did in 1 step. Yep. All right, so now that we've got the whole, hopefully, weight, mass thing cleared up, it's just because, guys, we just say things wrong, okay? Our culture, we say weight and mass are the same thing when they are not, okay? If you wanted to win the Biggest Loser, have them weigh you on the moon, okay? And you win because you've lost the most weight, even though you're still the biggest person in the show, okay? Right? Your mass is how much of you there is. If you're looking to lose weight, you're not really losing weight, you're losing mass. Indirectly, your weight decreases as your mass decreases. All right. Yeah, I want you to try this one. This is an inclined plane question, but it's still a potential energy question. Okay. So we got a heavy box with a mass of 35 kilograms pushed up a hill by a force of 150 newtons over a distance of 25 meters. Okay, so the hill, the ramp, this part of the ramp here is 25 meters long. Just redraw that picture so it makes more sense. Okay, so this part of the ramp or the hill is 25 meters long. Okay, what we're looking for is how much higher is it at the top of the ramp? Remember how I said that using a ramp makes work easier but doesn't make less work? Okay, this is a question that's kind of going to show you that more mathematically. Okay. Okay, so here's how we start out. Okay, work is changing the potential energy of the box. Everyone okay with that? Okay, the box is moving up the ramp. It's not accelerating up the ramp. It's just moving up the ramp at a constant speed. Okay, so do they give me a force and a distance in this question? Yes, they do. Okay, so I'm going to use force times distance for work here, okay? And then for change in potential energy, I'm going to do the same thing I always do. M times G times H final minus M times G times H initial. Okay, can I make this a little bit easier with the M times G times H initial? Yes, because what is it? It's 0, okay? All right. Now, all I have to do is figure out now how high the ramp is, because the whole purpose of a ramp is to use less force over a greater distance. Okay, if I'm just lifting this to the top, this is what I'm doing. I have to exert the force of gravity, m times g, over the entire height of the ramp, which would be a neat trick because the ramp is 10.5 meters, or it's almost 11 meters high, and I don't think I could reach that far. Okay, all right. So I need to manipulate then for HF. So all I have to do is divide both sides by m times g. Okay, so then we'll have our 150 newtons times the length of the ramp, 25 meters, divided by the mass of the box, 35 kilos, times 9.81. Okay, was this exactly like your quiz question? Yeah. Okay, don't overthink it. The work energy theorem really only works one way, and that's this way. The beauty of work energy theorem is once you learn the steps, they're all the same. All you have to do is decide whether it's kinetic or potential, okay? And then you're solving it the same way every time. All right, so when we do that, we should get 10.9 meters for the height of the ramp. Okay, so mathematically, not a difficult question. Getting to the math, that's the difficult part. And guys, honestly, that's where physics gets tough. Physics doesn't get any more mathematically difficult, really, than what you're doing right now. What becomes more difficult is getting to the math. Okay, some of my best physics students are the people who are like me and aren't all that good at math. Okay, but we can look at something and see what's going on and go, oh, right, that's what's happening. Well, I can get to the math then. I can do the math. I find that people who are really strong at math tend to be weaker at physics because they just want to see the math. But you have to get there first, okay? And that is really the big thing that makes a person good at physics, is being able to see the physics and do the math, rather than do the math but not be able to see the physics, okay? All right. Try this one. That's a basic, we did one just like this yesterday, okay? This is a basic one to do with what kind of energy? Kinetic, okay. All right, so we already said that the type of energy being changed in this question is kinetic. Okay, we know that the force that's causing that change in kinetic energy is 300 newtons. Okay, the distance over which that force acts is actually an arc. Okay, but it's the pitching arc, so it's 2.2 meters. We're looking for the speed at which he will release the ball. Well, when a pitcher starts his movement, how fast is the ball going? 0, it's in his glove. Okay, we have to assume that the initial kinetic energy of the ball is 0 in this question. So work equals the change in kinetic energy. So force times distance equals 1/2 mvf squared minus 0. All right, so we don't even need to bother writing that. Okay, then we just need to solve for the final velocity of the ball. So we're going to divide both sides by half of m, bring it over here, and square root. All right, so when we plug in our numbers, we have 300 times 2.2 divided by 1/2 times the mass of the ball, which was 0.250 kilograms. Okay, when we do that, we should get 72.7 meters per second. Okay. All right, that's a pretty basic one. The initial energy was 0. Okay, you just had to identify which type was being changed and then manipulate and solve, exactly like the steps say. Okay, questions on that one? All right. No, we've done one like that. Okay, I'm going to save a few of these examples. I'm going to save a few of them for another day. Okay, what I need you guys to do right now is take out your phone, page 25 of the worksheet package. Okay, these are much easier than the ones we've been doing. They start out with just work is force times distance. Okay, so they're much easier than setting them equal to each other. All right, that's where I want you to go. Okay, it's called Science 10, Work Energy Problems. Okay, page 25 of 33 on the worksheet package.
So we're only using work equals.
Well, no, for the first couple. Okay, and then it'll become FD equals the change in energy after that.
I don't know when to use what equations and how to.
You have to look. You have to read it and go, is it the change in velocity? Is a change in velocity happening? Then it's 1/2 mv squared. If it's a change in height, then it's mgh. Okay, that's that thing you got to identify from the question. Is potential changing? If it is, height's changing. If kinetics changing, velocity's changing. Okay, that's all you got to look for in the question. Then you know which formula to use.